Welcome to the third video lecture related to the topic numerical integration. The following slide summarizes what we covered so far about the topic. Basically, we saw the simple rules, the formulas that gives us the approximated value of the integral, as well as in red color, the formulas to bound the different errors with the different methods. Now we saw what are called the simple rules, and they are called like that because the main idea is to use an approximated polynomial in the whole interval AB. So if I want to compute the integral of the function f of x inside the interval AB, the simple rule methods approximate the function in the whole interval using a single polynomial. And that polynomial can be constant with the rectangle rule, a line, degree 1, polynomial with the trapezoidal rule, and a parabola with Simpson's rule. What we want to do today is to move to better approximations using the idea of the composite rules. Now, the idea of the composite rules is very simple. In the interval AB, where we want to compute the approximate value of the integral, we will subdivide in subintervals this initial interval AB. And in each one of these subintervals, we will apply one of the simple rules we saw. To give a better idea, let's start with the rectangle rule. If we want to use the composite rectangle rule, what we will start doing is subdividing the interval AB in subintervals. Okay, so somehow a way to plot this is that between my initial point A and my final point B, we will define here some more points, so we will have more subintervals, and we will apply the simple rectangle rule in each one of these subintervals. Now, I think this is a very simple idea that can be illustrated using Maple. Okay, in Maple we have something called tutors, and this one called Riemann sums. Now here, for example, I'm plotting the function sinus of x, which is this red function between 0 and pi. And what I'm doing here is, let's start with just one single interval, okay? If I start with one single interval between 0 and pi, then when using the rectangle rule, let's say the left rectangle rule, the value of the function here is 0, so that will define the height of my rectangle. The result is 0. However, if I use, for example, the midpoint value, the value of the function at the midpoint to define the height of my rectangle, then I will get this area as an approximation of the area under the curve. Okay. Now, of course, this is our very bad approximations because we are just using one interval. This is the simple rule. Now, what happens if instead of just using one interval, I use 4 intervals? Okay, now we can see the effect of adding more subintervals. I'm still using the idea to approximate the function with a constant value, but that constant value is only used in this interval, and then at the next subinterval I will compute again the value at the midpoint of this interval to define the height of this rectangle, and so on. If I use, for example, the left rule, then as the value of the function here is 0, this first rectangle will have area 0, but at the next one, the left side of this interval has this value, so this will be the area that will be computed. So we can see that when we move to composite rule, just increasing the number of subintervals, we can really improve the precision of this approximation. I can increase this, and we really see that the shape of the area we are approximating is each time closer and closer to the exact value. So that's the main idea behind the composite method. Now, n is the number of subintervals, and h is the length of each one of the subintervals, okay? Normally, we will use equally spaced intervals, but they could be different. So we will keep in general this notation, hi, that is the length of the interval defined by points xi, xi minus 1. Note here that we have points that go from x0 to xn, so n plus 1 points, so there are n intervals and subintervals, okay? Now I would like to move to the convergence of the rectangle rule. Now, we know that we can improve the error because we can make the value n to increase, to make it higher, which of course means that the length of the intervals gets smaller. So we can think that h goes down to 0. The length of the intervals is each time smaller, as we can see here in this. We can see that the length of each one of the intervals, as we increase the number of intervals, is smaller. Okay. And what we will do in this slide is to understand what is the error for the composite rules. Okay, so we will study the convergence of the error for the composite rules. Now, to do that, we will assume that we have equally spaced intervals. So we will assume that h is b minus a divided n. So h is the same value for all the intervals. Okay? Now, we know from the previous lecture that the error from the simple rule method, so the error from the simple rule method that will be committed in one of these intervals, because in each interval I'm using the simple rule method, looks like this. Yeah. The point here is that if I'm, for example, concentrated in interval I, then this psi value lies in this interval xi minus 1 xi. Now, I would like to know an expression for the whole error for the composite rule. Now, of course, the error that I will commit after doing n times the simple rule should be equal to the sum of all the errors committed by the simple rule at each one of these intervals. Yeah. Now, I will substitute this by this expression, yeah, because this is the error committed by the simple rectangle rule at each interval. So it looks like this, but now I need to use this subscript to note that they are different psi values in different intervals. So each one of these psi values lives in this subinterval. Now here we will use the mean value theorem to change this expression to look like this. Now the main difference here is that these psi are n different values of psi. Here we have one specific value psi that lives in the interval AB. What we used here is the following. When you compute an average, when you compute an average value, a mean value of some data points, what you normally do is, let's say I want to compute the mean of some n values I have, yeah? So let's say from I equals 1, try this to look like an I, okay, from I equals 1 to n, I want to compute the average of f prime ci. So I will divide it by the number of elements. Yeah. So if I want to compute the mean value, this would be the mean value of these data points. Yeah. What I will normally do is sum all this and divide by n. Yeah. Now, this mean value we will see that can be obtained by evaluating my function f prime at another point, saying that I don't know exactly the value, I don't know exactly where it is, but for sure it exists, and it lives in between a, b. And the reason for that is the mean value theorem. So we are using here the mean value theorem. And as we can see here, what we are saying is that if I have a continuous function and its derivatives accomplish different values inside an interval a, b, for sure the mean of all these slopes should be attained at some place. So for example, at a point psi, here it's called c, but it's this idea, okay? So the mean value theorem says that this point exists and is in between a, b. So using the mean value theorem, we have that this f prime psi is equal, or let's say that this part here, okay, this part here is equal to f prime psi times n. You can multiply this by n and it will come multiplying here. So yeah, it's like doing this in one step. Yeah, sorry about that. So what I'm saying here is that if I multiply this by n, then this gets multiplied by n. So this f prime times n is equal to this part here. Yeah, because this n, of course, is simplified. Okay? So this part is equal to n times f prime psi, and then h squared divided by 2 is constant, so it can be written outside from the summatorial, and we get this. Okay? Now, n, as we are assuming we have equally spaced intervals, n is equal to b minus a divided h, so we can simplify one h here, and we obtain this final expression for our error. So if you like boxing things, this is a good thing to box, okay? This is the final expression for the error in the case of the composite rectangle rule. And one thing that is important to note here is that f prime psi, b minus a, and 2 are constant values that do not depend on h. So we can think in this like a constant value that multiplies then h. And we will say that this is a linear method because the error will go down to 0 as fast as h goes down to 0. So when I make h smaller and smaller and going it tend to 0, I will see that my error diminish at the same speed, at the same rate, because it is linear convergence. So as we saw in other topics, linear convergence is, we always say this is slow. We could really try to improve that, and that's what we will try with the next method. Now, I will just summarize what we did up to here. We covered the composite rectangle rule, we saw the formulas to approximate the integrals, and we saw the expression for the error. And we saw that it is a linear method. Now, we would like to see the trapezoidal method, the trapezoidal rule, as we would like to improve this slow convergence of the rectangle rule. Now, the idea of the trapezoidal rule is pretty similar. We want to subdivide the initial interval AB into subintervals, and in each one of these subintervals we will approximate with the simple trapezoidal rule. And that's what we do here. We approximate the integral with the trapezoidal composite rule, which is the sum from 1 to n of all the areas of these trapezoids in each one of the subintervals. So the area of each one of these trapezoids is given by the formulas we derived in the previous lecture from the simple rules. Now, the main difference is that now this is not anymore A and B, but this is always the left and the right ends of the subinterval I'm studying at the specific time. Okay? And H now can be different in different intervals. So that's how the formula would look like. And if we assume that we have equally spaced points, so we assume that hi is always the same value, let's call it h. So what I'm saying here is that if they are equally spaced points, what I'm saying here is that h is equal to b minus a divided by n. Okay? So here I'm writing down each one of the contributions, and we can see here that fx1 is appearing in this formula, but it will also appear in the next formula because x1 is the right end of the first interval. Okay, so I have here x0, for example, and I have here x1, and let's say I have here x2. Yeah, what happens here is that x1 is the right end of the first interval, so that's why it appears here. But then at the next term it will appear also because it's the left end of the second interval. So that's why f of x1 will appear 2 times. In fact, all points will appear twice, but only the first and the last one will only appear once because they only live in one interval. The first interval for x0, the last interval for xn. So xn is only contributing into one element, the last one. Okay, so that's why the formula reads like this at the end. And we can also see how the trapezoidal behaves with the maple tutorial. In this case, we will use the trapezoidal rule. Let's switch to only, I don't know, 3 intervals, for example, or 4 intervals. And you can see how the trapezoidal rule is used in each one of the subintervals. Okay, so just clicking here, trapezoidal rule, and selecting here the number of subintervals. We can change the function, of course, here, I don't know, kind of x plus 1. I think that's one of the examples that are proposed exercises in these slides. So you can change the function, the value of a, b, the number of subintervals, and play a little bit with the options here. Okay? This is the exercise. I think you can try to do it by hand using the formulas we derived, and then you can check whether it is correct with the maplet. Now, what about the convergence of the error? Again, let's recall the error for the simple rule. The trapezoidal simple rule had this error. Now we want to derive a formula for the composite method. So this is going to be the sum of the contributions of the simple rule method n times, because we are using the simple rule in n different subintervals. So again, this is substituted by this formula, where now this psi, it's different in each subinterval. It lives inside in each subinterval, but again, we can use the idea of the mean value theorem. So here we are using again the mean value theorem. let me try to write that down here. So mean value theorem is used here, and that's why we can substitute this symmetrical in here by n times f prime prime at a point psi that now lives inside the interval AB. Now again we will substitute n by b minus a divided h, because we are assuming they are equally space points, and now we can simplify a little bit and we will get the final formula, which is this one. So if, again, I would recommend to box this. This is the formula to compute the composite trapezoidal error. And what we can see here is that now we have a quadratic convergence. So what's the meaning of that? That means that when h goes down to 0, my error will go quadratically to 0. So it will converge much, much faster than the rectangle rule. Now, summary of what we covered up to here. This is the formula to approximate the integral using the composite trapezoidal rule. And in red color, we have the formula of the composite error. Here using n, here using h. Of course, n and h here are related. Remember that they are inversely proportional one to the other. In fact, recall that we are assuming equally space points. So h is equal to b, sorry about that. So we are assuming equally space points, means that in the error formulas we are assuming that h is b minus a divided by n. Okay, in the error formulas. Okay. Also in these formulas to approximate the integrals, we are assuming equally space points. So when h has no subindex at all, it means is equally spaced. So h is b minus a divided n. Okay. Now finally, Simpson's rule. Same idea, but now in each subinterval, we will use a parabola to approximate the value. We can see how that behaves with Maple. In this case, we need to select Simpson's rule. Let's put only one interval and see what happens. Okay. Okay. You see, it's not able to do it with one interval, because in this case, we will change this option, partition type, to subintervals and check again. Okay, now one interval has 3 points for Simpson rule: the left, right, and the midpoint. So here we are just using one interval, so it's simple, is the Simpson's simple rule. Now we can use, for example, 2 intervals. Here we have a parabola, and here we have a different parabola. We can use 3, for example, and we will have one parabola going through this point, the midpoint, and the right point, and the same in each one of the other intervals. Okay? So the expression to approximate the integral is the following. We will sum from 1 to n the expressions that we got for the simple rule method, and we will add together and we will get this formula. You can see that I think this is very important, so I will try to plot it. When you use the composite Simpson rule, I think it's very, very important to bear in mind that the midpoints are somehow different to the others. When I plot it, normally I even plot them differently. Okay, so that's what I'm trying to do here. Let's say this is the last interval, and there's a midpoint also there. Okay, so let's say this is point x I minus 1, and this is point x I. Yeah. Now, one notation that I think might be useful and is used in these notes is that this point uses the following notation: x I minus 1 comma I. So this means this is the midpoint between xi minus 1 and xi. So this is the notation that is followed here. You see, this means this is the midpoint between x0 and x1. Or this one, for example, is the midpoint between x1 and x2, and so on. Okay? Now, the midpoints will be always multiplied by 4, because that is the coefficient that multiplies the midpoint. But the other points, xi minus 1, xi, the ones that contribute into 2 elements, will end up with the coefficient 2. x0 and xn, as only live in one interval, they have a coefficient of 1. Okay? So somehow, if you like boxing things, it's also a good idea to bear in mind this formula to compute the approximated value of the integral using Composite Simpson rule. You can try to do this exercise and then check if it's correct using Maple. Finally, we can study the convergence of the Composite Simpson rule following the same idea. We start from the formula of the simple rule, and then we try to compute the composite error by summing up the n different errors coming from the n simple rules applied in each interval. Again, we will use the mean value theorem, and we will get this formula, where C lives between A and B. Now, what we can see from this formula, oh, sorry, this is not the last, this is the last, already simplifying the H, okay? And what we can see here is that in this case, we have a fourth order method. So this is a very fast convergence. When H goes down to 0, my integration error will go down to 0 as h to the power 4, which is much, much faster than quadratic and, of course, than linear. Here we are plotting the error just to give you an idea, and if you just plot h versus the error, of course you will see that as h goes down to 0, your error goes down to 0, and it really looks like fourth order polynomial, but it's very difficult to appreciate here if it's a polynomial of degree 4 or a parabola, or it's really difficult. So that's why we will talk a little bit about the convergence graphs in a few seconds. Now, I would like first to show you this summary slide. We derived the formula to compute the Composite Simpson rule to approximate the integral, and we saw the error for the Composite Simpson rule. As you can see, rectangle rule is linear, trapezoidal rule is quadratic, and Simpson rule is fourth order. Now we will try to understand better this speed of convergence using the logarithmic convergence plot. Now, we say that an integration method has convergence order p when its error is c times a constant value times h to the power p. So when p is 1, we say the method is linear. When p is 2, it's quadratic. When p is 4, the convergence order is 4. Okay? Now, we know that if we just plot h versus the error, it's very difficult to appreciate where this is quadratic of order 4. So we will apply logarithms. This is not the first time we use logarithms to plot convergence graphs. And we will apply here the logarithm to the left side and right hand side of this equality, and we will get that the logarithm of the error is equal to the logarithm of this part. Yeah. Now I will use the properties of logarithms, and I can split this into the logarithm of c plus the logarithm of h to the power p, And of course, here we can use the properties of the logarithms that allow us to write this p multiplying here and logarithm of h. So if we think in this as what we will plot in our y-axis, let's call this y, okay? I will use like commas like this, okay? Let's say I think this is my y-axis, okay? And then in the right-hand side, let's think that this is what I will call the x-axis, okay? Now, what will happen here is that if this is the y-axis and this is the x-axis, what I'm plotting here is y, I will write it here, y equals p times x plus a constant value, c tilde. So this is a line. So what we will get here is a line, okay? And the slope of the line is p. So if we use the logarithm scale and we plot logarithm of h in the x-axis and logarithm of the error in the y-axis, we will always get lines, and the slope of the line will be the order of convergence of the method. That's what we did here. We are plotting the logarithm of h in the x-axis, the logarithm of the error in the y-axis, and here in blue and green we have the rectangle rule, and the slope in this case is 1. The pink line here is the trapezoidal rule, so this slope is 2. And finally, in red color, we have the Simpson rule, which in this case, it has a slope of 4, okay? So this is what I wanted to cover today. This is the theoretical, this finishes the theoretical part of this topic. I will propose you some exercises to really make sure you understand everything and you can solve the related exercises. See you!